get your seat there, and we're going to shift gears a little bit. It's not a total departure from my introduction here. We're going to still be talking about some innovative things. In this case, to do a step change in efficiency to make up for what carbon capture might require. And we'll start off with that nice photo there from the Olympic flame. By the way, see if you can think this through. Can you think of anybody that during the upcoming Olympics, just one person, will spend most of the Olympics thinking about combustion? Me? No, I'm going to be busy watching those guys do their thing. I like watching the Olympics. Anybody?
The one who keeps it running?
Exactly. The guy who's responsible for that flame. You don't think about it, you know, until you're a combustion engineer and you realize, you know, there's a guy that designed that flame, and he had designed it so that if a thunderstorm comes through there with a 60-mile-an-hour wind, it doesn't just blow out and then they got to relight it and it's a mess, right? You know, you can't do that. I had the privilege of meeting the guy who was responsible for the flame and the torch, you know, the one that they run with. And they carry that thing around. It was an interesting, we were having dinner and it was an interesting discussion. He's a combustion engineer, right? He works for a company that sells burners. And he got that job. This was in one of the past Olympics. And it was just a fun thing to think about that there's actually some combustion engineer who's a student just like one of you, and he had to design that thing, and then he had to work with the guy from the arts department to make it look nice, right? I mean, it's got to look Olympic. And then they weren't happy because they didn't like the way the soot profile was coming out of the top, and you know, they went through that. And anyway, so just some things. Now you're going to watch the Olympics and be thinking about that flame, right? You'll turn it on and you'll sit there with your family or friends and say, did you ever think that the guy... No, they don't, family and friends, they don't understand, but anyway, you do. So here we go. Next session here, we're going to talk a little bit about making a step change in generator efficiency through pressure gain combustion. How many of you have heard about pressure gain combustion? Let's see if I got any takers on that one. There's at least one or two, so for the rest of you, this is new and it'll be a lot of fun, I hope. Well, this goes back to that slide that I put up a little bit ago. I put a big banner through the middle just to sort of remind you what we're doing here. You know, we spent a long time looking at chemical looping combustion, which really puts that CO2 capture process inherently in the generator. All right? It's got limits, though. We were talking about that at the break. It's limited by a steam cycle, the way I described it. So we can only do, although we can get rid of this term with chemical looping, almost, you have some compression work, you're kind of limited in what you can do over here, at least for the way I was describing it to you. So let's look at some other technology where maybe I can jump up this term dramatically. And when I say jump it up, it's got to be a big number to compensate for over here, like 5%, okay? How am I going to do that? Well, that's what we're here to talk about. You know, right now, most generating capacity on fossil fuel is just migrating to natural gas combined cycle turbines because natural gas is cheap and those systems, combined cycle, are highly efficient and they're relatively inexpensive. Gas turbines, of course, are a major part of the transportation system for aircraft propulsion. They've been developed over a long period of time. Advanced cooling, techniques in the blade for the turbo machinery allow you to get to really unprecedented efficiencies, right? I think you know that, but that's what's going on in the gas turbine business. I put up here today just a little bit of history to highlight that. Today you can buy a combined cycle gas turbine more than 60% efficient, which if you would have told me that 20 years ago, I'm not sure I would have believed it. It just seems amazing it can be done. Here's a plot that I put together for some literature cases showing the efficiency of gas turbines introduced over the past, dating back quite a few years now. And I was surprised when I put the plot together. It's just about linear, the efficiency gain of about 0.5% a year. And so, I asked the question, well, can we do a lot better? Can we make some big jump in efficiency? And the first thing you got to think is, well, how high could it go? Right before I say I want to try and make it better by improving things, I better know what I'm doing, how high can I go to. So if you just say, well, even with a state-of-the-art turbine, The Carnot efficiency is 84%. It's way above that line. So at least in theory, I could jump above that line somehow if I were very clever. There's quite a bit of room to go yet. And the question is, what do you do to jump above that line? So let's take a little quiz here, get your ideas out together. You know, the conventional combined cycle, you take a gas turbine, you have a high efficiency gas turbine here, you take the exhaust out at about 700-800 centigrade and run it through a steam generator, run a steam cycle on the bottom, that's pretty high efficiency. You can do even better if you make the temperature and pressure here higher and improve the efficiency there. We can do all those things. But what if you were given the job, you finished your PhD, you started a new company, and said, oh, we need a 5% gain in efficiency, and we don't want it when you retire, all right? I want it now, all right? So what could you do? All right, it's a great thing to think about. I got any new ideas there? Well, there's a lot of ideas out there. There's quite a few people right now looking at supercritical CO2 steam cycles to replace that. There's a whole bunch of reasons why that might make sense. I'm willing to wager you're going to see some of those things added to gas turbines over the next few years. One of the ones that I really like, well, I'm struggling to keep it funded, is just replace the combustor here with a fuel cell, a high temperature fuel cell, make it a completely different combined cycle. You can get to unprecedented high efficiencies that way, but you need a big fuel cell, which we don't quite have yet, but we're getting close. Maybe you go find a different thermodynamic cycle, something that hasn't been thought of before. Maybe that's a way. All right? And then my personal favorite is make the turbine blades out of diamonds. And if you are successful at that, I would like you to hire me because, well, you're apparently a lot better than most of us, because I don't know how you would get enough diamonds to do that and then sell them. But if you're currently in the business of fixing gas turbines and operating them, you would swear the blades are made out of diamonds, given the price that they're currently paying for them. They are pretty expensive, right? But you're probably not likely to suggest that one. So you got any other ideas when we look around and pause for a minute? What might you do? Anybody got a thought?
Increase the pressure ratio.
What's that? Pressure ratio and temperature. That's the way it's being done. I think there's still room to go there. That's how we're going to proceed with this, is get the pressure ratio and the temperature ratio up in a combined cycle, because you still have heat at the bottom of the combined cycle. That's one way. Anybody else? Go ahead. What's that? Move to some other cycle, not limited by electrochemical, which would be the fuel cell one. Great idea. Me and you are going to go have dinner or something, because that's the one I think really makes a lot of sense too, but you got to develop that fuel cell. It's a great idea. A lot of thoughts there. Maybe some others. Anybody? Go ahead.
Reduce the bearing friction inside of the turbine itself.
There's a lot of people working on now secondary systems in turbo machinery. I was visiting with some people from Pratt, and they said, we've done a lot with the hot section and the efficiency of all those components, and right now their focus is really on how do you get all the secondary systems to cooperate and have higher efficiency there. Things like the cooling through the hub area and stuff like that. It's a great suggestion. There are people pursuing that. The one that I'm going to, go ahead, one more and then I'm going to move on. What's that?
Blade cooling.
Blade cooling, a lot of work on that. That allows you to get to that higher firing temperature along with a higher pressure ratio. Somebody said that's what's being done. But the one I'm going to talk about today, and the reason I'm pausing on this and pausing on it, so you remember what I'm saying here, is a different thermodynamic cycle based on combustion. It's a combustion group. So I'm going to say, hey, I'm going to change the cycle based on combustion. Let's see how you do that. Pressure gain combustion. By the way, this particular graph demonstrates why I chose not to pursue graphic arts as a vocation. Right? Best I could do here in short order. But I'm trying to represent a flame inside of a combustor. Conventional steady combustion. There's the flame sitting in there. The air is moving through there. You're coming in into gas turbine condition, 30 bar, 600 Kelvin, and move through the back end of the device and have that temperature rise. And of course, the heat that I put in is equal to the change in enthalpy between those two stations, and that's what lets me generate power further downstream. That's what happens in gas turbines today, and you're probably aware that there's a big irreversibility connected with constant pressure combustion, right? So I could do the process different if I thought about it a little bit, like, well, why don't I just keep the combustion in a closed box? So then the heat that I'm putting in, same heat, goes into the internal energy, not the change in enthalpy, right? So the conditions in constant volume combustion, you get to higher pressure and a higher temperature, right? So now the trick is, how do I use that higher availability energy? It's the same energy, it's just at a higher availability, right? So I got to figure out, how do I get it out of there in a thermodynamic cycle that I can operate? And this is where probably all the work in pressure gain combustion is really focused, because I can get to that initial state, but if I simply allow unrestrained expansion, just blow it out through the side there, I just go back to the original constant pressure condition, and there's just no benefit, right? So what I have to do is figure out, how do I capture that available energy and turn it into useful work, and that's what pressure gain combustion attempts to do. It's a different cycle, all right? Conventional gas turbine, you come out of the compressor, go into the combustion chamber, and there's typically anywhere from 3, 4, and even higher percent pressure loss as you go through the combustor. Just the pressure that's needed to drive cooling flows, drive mixing, all those things, you have a pressure loss. And you're talking about the working fluid of the cycle, so that pressure loss is very expensive in terms of cycle efficiency. All right? You'd like to get rid of it. Well, in pressure gain combustion, the idea is the pressure actually goes up from here to here by some amount that we're going to have to figure out how to engineer. And that can jump the efficiency of the process up quite substantially. You're going to see that in just a moment. So this is the idea. I'm changing the cycle, but really I'm focused in on the combustor. The rest of the process looks familiar. What goes on in that combustor is where all the engineering, where all the innovation is going to occur. This is not a new idea. I apologize, no truth in advertising. We said new ideas in combustion. It's not new. It's just the drivers are new, and I will show you at the end there's some new developments that I think are going to make it possible. It goes back, first of all, you actually attempt in some piston engines, right, to have constant volume combustion and then expand from that high availability. That's why a small piston engine has a higher efficiency than a small gas turbine. That and some other issues connected with component losses. But they try to capture that reality that people understand. You want to do constant volume combustion to reduce irreversibilities. There were some early gas turbines. This is how it was termed, the explosion turbine. A guy named Halsworth. I pulled this photo from a journal in 1922, and I love the caption there. The Thyssen-Halsworth oil turbine may be the power of the future for future merchant ships. And that was 1922, and here I am telling you we're trying to develop this. So he was just off by just a few decades, okay? But I think it's worth going and developing this today. It was developed at that time, and in fact, went on to be developed for compound piston and turbine engines. This is the so-called Napier Nomad engine of circa about 1950. And what you see here is turbo machinery dumping out into a piston engine and then expansion through the exhaust, much like a turbocharged engine or turbocharged engine that you're used to seeing today, except the intent was to get shaft horsepower for driving a propeller out of that. Now, it wasn't a bad idea, and at the time it had the greatest specific fuel output, in other words, greatest fuel efficiency of any engine that they had, but it was a maintenance nightmare. You have these two engines operating together, a piston engine, now at a much higher ambient pressure, right, because you're pressurizing with this turbocharger, trying to get power out of both shafts and couple them together. They flew it for a few years and said, maybe there are some easier ways to get to high efficiency, which was definitely true in 1950, right? I mean, there was a lot of room to go in terms of firing temperature in turbines, pressure ratio, compressor development, so that's where the focus went. People pretty much walked away from this as a notional idea because they could see this is going to be hard, this idea of constant volume combustion, and I can make big improvements in current technology with constant pressure combustion. So it just begs the question, so why are we talking about this now? Why are we looking at this again? All right, and these are some quotes we got from, this interview was actually published in the Technology Review from MIT. This is Mike Idlechek. He's the VP of Advanced Technology at GE Global Research. And I'll just pull that state out in the middle there. You see, we see the potential 30% fuel efficiency improvement for a flight engine. is one example. I mean, that's just boggles my mind. 30% improvement. Remember the example I gave about driving my car? It's like discovering new fuel, isn't it? So let's hope we can get there, right? And then he says for ground-based power, you know, efficiency gains anywhere from 5 to 10%. Remember what I said the penalty for carbon capture was? 5 to 10%. Here I'm saying I can make it up. And he points out here, well, you know, if you wait and we do all the cooling technology, we think we get there. No other technology can get that far all at once, one shot. That's why he's interested. That's why I'm interested. He says the first application will be land-based. Yeah, well, frankly, I didn't want to sign up to be the first flight application, okay? So he's right there. If we get this to happen on ground-based power and succeed, it'll go into flight application, I'm sure of that. At Rolls-Royce, I didn't hear this quote, but my friend Fred Schauer did, and he said, if you get a 5% pressure gain, it's just like lopping off a compressor stage. It's just incredible, right? That compressor takes up a lot of energy to spin, plus the engine can get shorter, you know, assuming the combustor is comparable length. A lot of reasons why you might want to look at this. So it's one I wanted to bring to this audience because maybe some of you will work on making this a reality over the next few years. There are a number of people looking at this as a technology, and there are different ways to approach pressure gain. And this afternoon, I'm just going to take you through each one and tell you kind of where they're at, how they work. You can think about what are the combustion issues that need to be addressed. I'll go through the work going on at NASA. Glenn came and just doing some work. We did work on this back in '93 in my lab. I was very much involved in it myself at that time, and I'll explain that history in just a few moments. General Electric, as well as Rolls, is not on here, and others are actually working on this. Unique process going on with Rolls Liberty Works and Purdue, and this one at the bottom I'm going to talk about, which is, I think, really the motivation for why we said we needed to get back into this in a hurry. So let's talk about first one of these called pulse deflagration combustion. Just need a drink of water for a second. As I mentioned, we did work on this at NETL, so I borrowed it heavily from that earlier work just because I was familiar with it, although I'm going to talk about work going on at these other places as well. So for pressure gain combustion, there's an easy way to do this with little mechanical complexity. It's called an aero valve, and I'm showing the schematic of processes that go on that allow you to have this aero valve pulse combustion, and the idea is to just do the combustion in a chamber where you control the size and the length of the inlet and the exit. So combustion starts here. It's a pressure rise. It drives gases out of both ends of the device. But by making this end longer, conceptually, I think you see what happens. You have enough momentum to actually keep going, draw in fresh reactants, recompress as the waves come back, and then combust again. That's an interesting process because you think, well, why does it favorably want to go in one direction or the other? Right? But it does, and I'll explain why in just a few minutes here. So we put an experiment, and this is going back into a long time ago, 1991, and we put a combustor in a chamber like that. The combustor was made out of pipe fittings, not because we couldn't afford to do machining. Take a guess why we made it out of pipe fittings. No guiding theory. Nothing. We didn't know what geometries would allow pressure gain. So we knew we were going to be going through a lot of geometric changes, so we just said, let's make this easy, start doing this. I was very frustrated as a pretty recent PhD. I thought, isn't there anything to guide how you do this process? So I put together a zero, sort of 1D model, very simple. I didn't even put the citation up where we published this because it was so many years ago I was embarrassed. Well, it doesn't sound that good anymore. I'll explain that in a moment. But we did put together a model, found all these characteristic times, solved the conservation equations, and you're probably thinking today, well, why didn't you just model the thing? What was wrong with you? I don't think all of you as young people realize the progress in computational modeling that has gone on just in the last 2 to 3 decades that's really enabled, was the phrase computational engineering, I think, that was used just a little bit earlier. I would have loved it if we could have simulated this, but the computer wouldn't let us do it. So we came up with these very simplistic models, and we did a lot of experiments. And I was actually pleased. It might not look like good agreement to you, but we were able to predict the RMS pressure of the oscillation, experimentally modeling. You can pick up some of the trends there. we weren't quite as good in terms of the pressure difference. This case happened to show a pressure loss running through the combustor. We then used the model to predict what we needed to change geometrically. And here you can see negative here means we were actually gaining some pressure as we went through the combustor. It wasn't a lot, 0.45, but it was a lot more than the 4 or 5% loss that you get in conventional combustion. We thought, oh, that looks pretty good. And at least tempted to try now, what can I do in a more realistic environment, a high pressure combustor? So we basically built up the same thing and we put it in a pressure vessel, ran some tests. It was, again, a very similar design. And it worked more or less. We were able to model it, but we didn't get much more pressure gain than that, maybe 0.5%. We found out how to scale that. We learned all the things we needed to. But 0.5% didn't sound that good relative to the gains we were projecting going forward with advances in cooling and increases in firing temperature and pressure ratio. So frankly, we had a hard time rationalizing continued support. And the other thing that happened, completely unexpected, right at that time there was an explosion in the application of lean premixed combustion to turbine engines, which if you're following Tim Lewin's course of the last 2 days, dynamics problems galore. We were perfectly situated to address them, and we started to. We were working with a number of OEMs, solving dynamics problems. It was really an exciting time because we were doing so much work to address dynamic problems. Because we'd started on this problem, which is, again, unsteady combustion. Figured out how to solve some of those problems based on this work. So we didn't pursue it a lot more at that time. There were just some challenging problems that persist today, and I'm hoping that there's somebody here that's smart enough to take some of these on and still address them, because this is still an active area of research. I'll show you in a couple of slides here. But to be effective, you need to predict a design that's going to produce oscillations, and the progress that we've seen in premixed gas turbines makes that relatively easy. If you ask me to build an oscillating combustor, I guarantee you I can do it. We've done it a bunch of times. But I can't always predict where it's going to oscillate. That part's harder. The other thing is, it's not just oscillating. You've got to predict a design that also has a pressure gain. There's no guiding theory even today to do that I know about. It. Maybe somebody will prove me wrong, but there just isn't. How do I come up with a design from the get-go that has a pressure gain? You know what? CFD is the enabler. For those of you who are doing computational combustion, this is a great problem to try and figure out how do I do the design to come up with pressure gain. We just don't know that easily, but I hope we can figure that out. Another challenging problem with this is you need to capture the energy that's in that unsteady flow. Remember I said that earlier on, right? You can't just let that flow expand and not turn it into useful energy. You got to put it into a turbine somewhere to actually use the energy. Luckily, Rob Miller at Cambridge is working pretty aggressively on that particular topic. He gave me these slides. They have a facility where they impose unsteady flow onto the turbo machinery, and they're looking at how does that transition from unsteady flow to the turbo machinery actually affect the pressure gain. And these are plots from experiments that they did, and the color scale that you see there, it corresponds to the pressure gain. So 0.1 is like a 10% gain. There's 10% there. So there's a couple percent gain in here. And you can see here that gain actually survives through its passage through the blade in this case. But here it's actually destroyed. And as he explained it to me, it's due to the interaction of the vortice from that unsteady flow arriving in that turbo machinery. And you lose the gain that you had produced. Now he did tell me, as we communicated about this, they've changed blade designs. They think they can get around that. So there's a lot of encouraging results that tell you we think we can actually recover that unsteady pressure energy. We'll see how we can do going forward. I have to mention my colleague Dan Taxin's work at NASA Glenn on a shoestring. He would affirm that if he were here. But he has worked this issue of pressure gain combustion, in this case with a valve pulse combustor. And you can't see the combustor inside of the rig here, but there's a sketch of the rig itself, and he's done some simulations of that. He's one of the few people that's actually put it inside of a turbine system, albeit a very small one. I mean, literally, it's an automotive turbocharger. We replace the combustor with, this pressure gain combustor, and he's actually achieved some nice results. There's almost 4% pressure gain at a temperature ratio at 2.2, and he's actually, because he's looking at aerospace applications, he's busy looking at emissions. as well. So interesting work going on at NASA, and we continue to have a dialogue about how we bring this up to a full-scale application. So this is deflagration, pressure gain, combustion. Got a question here? Yeah.
Does the size for going to the smoke, replacing the smoke combustor, going to power plant plays a role in this concept?
Yeah, how do you scale it up?
Yeah, that's the efficiency scale up. Because I think gas turbines on the other way, go smaller sizes efficiency grow.
Yeah.
So how does
I think here you would see, as you went to larger scale combustor, less losses because you have less surface area to have frictional losses. I think that's what hurt us when we did pressure gain combustion in a pressurized environment on a small combustor, right? A lot of surface losses, a lot of frictional losses that we just couldn't manage. Go to a full scale engine system, it gets easier to manage those type of losses. So I think you're better off having a full scale one. We don't have scaling laws for these devices, but we do now have CFD where we can go up in scale. And that's what I would encourage this audience. You know, if you're able to get involved in this area, we do need to do that scale up and look at how losses change. Great question. So that was deflagration, combustion, pressure gain with a deflagration, meaning not a detonation, right? There's a whole other field where you try to use detonations to achieve pressure gain, right? And you know, as I've got it up there, the idea is that detonation essentially traps the combustion products behind that advancing front. So you get very high pressure gains in that region behind the detonation wave. And so the potential benefits here are substantially larger. I mean, huge increases in efficiency. I don't know that this is true, but maybe somebody could help me find any exceptions to that. This might be the only constructive applications of detonations that exist, right? Because usually you think of detonation, you're trying to bust something, right? I'm not aware of any others, but here we're actually trying to take a detonation and do something productive with it. So we'll see how well we can do here, but I think you'll see it is something we can achieve. So here's a typical cycle here, just so you understand the process. You have a tube. These things actually, you close the end of the tube. You fill it up, close the end, and then you actually do something to ignite the mixture, and then you have to actually go through deflagration and detonation transition. So you have a detonation wave in that tube. It travels out of the end, and then you have a rarefaction that empties the tube so you can fill for the next cycle, right? So that's how the process works. It's really pretty simple, but the trick is you have to get it to detonate. You can't have a deflagration going down there. You'll get very little pressure rise, right? So let's see how this actually works. There's been a lot of activity at the Air Force Research Lab on this concept. This is actually a rig, and the picture's a little bit hard to make out. There's a valve train assembly here. You can't quite see that there are 4 tubes in a row. Maybe you can look closely. These different tubes are each one detonation tube. There's 4 of them arranged that way. And literally, they took an automotive cylinder head, drove the valve train with a motor, right? So that became the valving on the back end, and then used a spark plug from that opening, right, where you got the cylinder head for the point of ignition. I wouldn't say they used a conventional spark plug either, but that's how they started the detonation. And then you can see, you know, the detonation combustion coming out of the back end. I suppose you really don't want to see combustion coming out of the back end, but you're going to get some burning still occurring out of the back end. And that is a very simple way to go to propulsion, right? No turbo machinery, just have boom, you know, a detonation come out of the back of the device. It's going to have propulsion. It works so well that you know, they're able to actually put it behind that aircraft, and that is a man-rated aircraft. You can't see the pilot's head, but it's been flown by a pilot, and I think that's just remarkable. And I really want to credit, he's not here to hear me say this, but you know, Fred Schauer has been the guy that drove that forward with much opposition and many naysayers. So he really was able to push that forward and show it could work in a propulsion application. A key scientific issue is trying to optimize the deflagration to detonation transition, right? You don't want to have the detonation finally emerge here because you're not going to get much pressure gain. You burn most of the fuel at low pressure conditions. You want, boom, high pressure detonation, bang, out of the end of that tube. So that's what you're trying to do. Question, yes?
Yeah, I guess I'm confused why you need to pulse. Right, so can't you like set up a standing shock wave in the combustor, right? So accelerate the compressed flow and then have, rather than have to pulse and open and shut this thing over and over?
Again, the thing you're trying to capture is the combustion in a fixed volume and then let it expand. Okay, so you wouldn't have that option in a steady flow device that I can think of, right? You've got to not across a shock wave. No, you're going to get a loss in stagnation pressure. Right? Here you want to hold the combustion in a box, fire it, and then let it expand. Okay, you want that heat release occurring in a constant volume environment. It's that simple. Right? I'm not aware of any other geometry that you could do it in that would be steady flow. Right? I just can't think of it. I mean, I'll think about that idea, see if I come up with something, but again, if you have a shock wave in there, that's a loss of stagnation pressure. Right? If you're saying you could hold the detonation constant and move the fluid through that, I have to think about how you could do that. I'm not sure how you would arrange it. All right. Let me jump on to the fundamental of this, though, because this is a key point for all of you. All right. Look at this quote from Venkat Tandarelli. Single combustion model to cover all the regimes of turbulent flame which are encountered in these things, it is yet to be established, which is a gracious way of saying we just can't model that system. Right? You just can't. Just think about what you're trying to do. You're trying to go from a deflagration to a detonation, and you started that with a spark and low-speed flow all the way out. You got to capture all that physics. It's a very hard problem to do computationally. It's a tough one. A lot of the development has still been empirically, but you all are going to make that a thing of the past, I'm sure. Right? We'll be able to simulate that process as we go forward. I talked about pulse detonation as a technology for direct propulsion. That's not going to generate electrical power because you need it in a power cycle. Right? So you have to take that energy and actually put it in a turbine and spin the turbine and recover that pressure energy. Tough job. Our friends at DARPA and the Vulcan project actually have taken that on to integrate that concept. By the way, this is called the Humphrey cycle, the detonation cycle. And so they've tried to move this technology to replace that combustor with a pressure gang combustor inside of the context of a turbo machinery. And remember that 1922 quote? See, he was just a little bit ahead of his time. And you know the future. They're trying to put it in marine propulsion applications. By the way, this program, the DARPA Vulcan program, I'm told is just declassified. But I don't know what I'm still permitted to tell you about yet. All right? But if you're interested in this area, a lot of that information will be coming out. You're going to just be amazed at how much progress they've made in this program. I don't know they're going to get funding to go to their intended application. Just telling you what's happening right now. But I expect a lot more information to be coming out of this program as we go forward in time. And as I said, if it does, I'm hopeful that people will report in the public literature what's been going on. It's really amazing. But anyway, the idea is to combine the PEE with turbo machinery. There are people reporting some aspects of this work in the public literature. I just give you one example right here. You can go look that paper up, and what you can see here is there's the pulse tubes right there. This is actually connected to a piece of turbo machinery down here, and this particular group at GE Global did 144 minutes of operation with these pulse tubes driving a turbine downstream, and their key point was to try to figure out how did the unsteady flow affect the performance of the turbo machinery, and they really surprised me. It was pretty good performance. It really wasn't. They were almost indistinguishable between steady flow performance and what they got with this unsteady flow. I will caution you, there's more details in there that you're probably not going to pick up just what I just told you. They didn't have exactly the same turbo machinery you get in a conventional engine, but the point is, it looks like you can get the energy out of that unsteady flow effectively. Now, I want to talk about this one. It's yet a different concept for achieving pressure gain combustion. And this is Razi Nowell from Indiana University of Purdue. And he and Phil Snyder really worked this issue. Phil's at Liberty Works, Rolls-Royce in Indianapolis. And the idea here is a little bit different. This is not a detonation combustor. It's actually a fast deflagration. but it relies on the same idea of constant volume combustion. And the way this works, here's air coming into the, this rotor device. That rotor spins, as I have it shown here. There's an end plate here that's got an opening just in that region where you can see there's an entrance opening up in here. And between those two, there are long tubes or channels, all right? And those channels rotate in front of those openings. So that rotating drum, all right, has a tube in it that alternately hits an opening on the inlet, spins through, and then goes to the outlet. Does that make sense what I just said? You got to catch that part. So now if I saw that thing apart and unwrap all those tubes, they end up looking like this. Here's all those tubes running this way, like if I just cut that and unwrap it. Here's the inlet on this side. Here's the outlet over here. And all those tubes are running up in that direction. And what I do is I flow air into those tubes. All right, that air is actually then carried, that channel is actually moved past the point of closing. All right. By the way, I'm sorry, I said air. I meant that's cooling air. This is fuel air mixture, the red. So that's flowed in here. Then it rotates past the closing point, and it bumps into this igniter, which then lights it at this end, and a flame starts propagating across that way. And you can see what happens is it bangs into the wall at the front end. You have confined combustion, right, as it completes combustion moving up into that end. It swings around to this side now. I go right up the top and into the bottom, and it meets the outlet. So what have you done? You've had confined combustion in that tube, all right? You fill it through that one port, ignite it, it burns in the other direction, and then you swing around the other side and let it go out, and sure enough, it creates a gain in pressure. And it's mechanically very interesting, right? It takes a couple of looks to get used to the idea, but you know, there's no reason why that won't work. By the way, that rotating drum, it has nothing to do with the turbo machinery, right? You can spin that any way you want. It doesn't take a lot of torque to move it. It's not providing any work. You're just moving it past the opening and the closing. And there's some advantages, you know, that I think are real advantages. You know, there's actually no mismatch in terms of the load on the different parts of that rotor. There's just a number of things that are big advantages of doing it this way. What are the disadvantages? You got to seal it, right? You got this rotating thing. It's got hot gases in both ends. It's got to swing past an opening and a closing. That's not impossible. There are devices like that. It's just a complication. It makes your life a little bit harder. So we'll see if we can address that. Dr. Nallum and Dr. Snyder, you know, we've met with them a bunch of times. We feel like they've got the sealing issues under control. They have actually run this device, by the way. This is at the Purdue lab in West Lafayette. It does not have integrated turbo machinery on either end, but they have actually run the rotating part of the device, and it's a fun movie to watch. It works very interesting. Yeah?
How do you change the mode on that? It seems like it only has one speed and it wants to run at the same speed.
Don't forget, you still have the ability to change the fuel-air ratio, just like a conventional combustor. That'll change it. You can change the speed of rotation, right? So that'll determine how much heat can come out of the device, right? It's going to burn in that chamber until it gets around and releases it. You can't do anything with it. So then it's an interesting controls problem, how to control the speed of that rotation. But you're asking the right questions, right? Because you want to know how do you control this thing. First time I heard it, I was like, I don't know, can that work? And then the more I started looking at it, the more I warmed up to it. You know, I think there's some real upside here. It's way different, way different than what people are used to doing. No other questions? Let me keep going here then. So, you know, this is a combustion group. I want to just point out what are some of the combustion issues that are involved in actually making this into a technology that works. Well, we just touched on it, right? You've got to get the flame to propagate. This is from the back wall as the rotor is moving by. Notice, you know, we're showing there's the injector where the ignition is going to occur, and you know, it's gradually the thing is moving by. So you have to make sure you get it lit, sustain a flame, and then it can propagate all the way to the back end before you get to the next cycle. So Professor Nallum he's actually been studying that, a very neat experiment where you can look in and watch the flame propagation in that environment. And the interesting thing, you don't think about this until I tell you, don't forget, it's spinning in that direction. So there's actually an interesting centrifugal acceleration or an effective G-force that acts on the flame as it's trying to propagate. This is interesting combustion fundamentals. Yeah?
Is it possible for this to detonate as well?
You know, it is possible, but there's no need to do that because you've got constant volume combustion in that environment. Detonation wouldn't add anything more to that. So this gives you the advantage that you don't need to detonate it, right?
Could it go faster then?
That's a true statement. It could go faster if you're willing to do it. Detonation pressure rises are a lot higher, though, you know, in terms of the spike, and then you have to convert that to work. This is a lot smoother. You have a lot more steady flow arriving at the turbo machinery here than with some of the other processes. Go ahead.
When you say faster, you mean frequency of reburning the volume, the rate at which you can heat fire.
Yeah, the speed that it takes you to go down that tube, you could spin that thing a lot faster and get more tubes firing, right, if you were detonating in that region. Yeah, good questions. Anybody else? Okay. I'm sorry, go ahead.
Just a previous section talked about detonation. The third point would be the energy of need to initiate detonation. It's not previous.
That's right.
About 20 times, I guess, the electrical requirement for the initiation.
That's right. You need the right pre-det device, which I actually won't get into how that's done, but there are devices that are built, and I'm not going to say how they work. They can actually lower the energy required to initiate detonation, and that was actually one of the tricks that was done that made some of this possible. I'm going to get back to that again in just a second. So if I forget to say something about how to initiate detonation, remind me later when I go back to detonation. Great comment. You guys are on top of this stuff. All right, let me move on here. Oh, I'm right back to detonation. You were leading my talk here. This is great. So I saw this one about 2 years ago at a DoD conference, and I thought, oh boy, we got to take a close look at this for ground-based power because this looks like it has some real upside. I'm going back now to detonation, not deflagration, but detonation to create a pressure gain. And this idea of having a rotating detonation wave inside of a combustor has been in the literature for actually a long time. It goes back into the 50s. I know we've got at least one person here from Ukraine. I don't know if you did. I know in Russia they did some work on this. Never really caught on. I'm not sure it was done correctly or not. Well, it's being done now. And the idea here is that you can actually take the flow from, say, the turbine compressor, run it into an annular combustor, and then drive a detonation which runs in this direction around that device while the main flow is going out the other end. All right, so let's look at what's happening right here just to make sure it's clear what's going on. This is the head end, and I'm showing it as, you know, this dashed line right here. There's actually, you know, some holes that serve as injection points. So fuel-air mixture coming up through that region. Combustion front, this is conventional deflagration. You'd like not to have that, really, but the detonation wave is continuing to move through the reactants in this direction. And so if I get that to consume most of the fuel as that detonation wave is zipping around, then I can get a pressure gain. The very interesting point here is the flow coming out of this end, because the way you have the way you configured. Will that stop? Hang on 2 seconds. Look at that picture and see if you can figure it out while I'm redoing here. Dead battery. Okay, now we know what's wrong. Left key handheld light. I don't know if he's okay, everybody stretch for a minute while I find a mic. Three? Yeah, okay. We got it. Thank you. This is going to be a challenge to hold this for the next how long. When do we quit? 45 minutes, all right. This is almost the last one in this section. We'll take just a quick stand-up break one more time here, but this one is so fun, you want to pay attention to this one. Okay. So I described what's going on here. The flow is virtually steady coming out of the top end. I'll show that in a second, just due to the way you diffuse that the unsteady products. So, this has actually been operating. I'll show you in the next slide. The simulation's going on at NRL. And, a key point here is, how do you start it, right? This one has a bit of an advantage in that once you start it, you're in good shape. You still got to worry about how you start, and I won't tell you the trick on how that goes, but it is not easy to start. And now I'm going to have my mea culpa here, because you ask me about, well, why can't you keep the detonation in there steady? This is actually approaching what you had just suggested. I mean, I'm just realizing that now as I'm presenting it to you, because you're keeping the detonation inside this chamber, right? It's not going out the end. And so it approaches what you had suggested, but it does it by moving the thing around in an unsteady sense in that direction while the main flow is going through forward. And so there you go. See, you were just ahead of the times there. It was a great thought, and these guys have figured out how to do it. So I apologize, I didn't think of that when you first asked me the question. But here we go. Let me show you what this actually looks like. Please switch. There we go. Okay. Now, hopefully this will work. Can't get all three going at the same time. We'll go a couple each here. So the CFD graphic that you're looking at, that's a simulation of the detonation running around, that annulus. And this is a view looking up the end of an actual experiment. And so you can see that, combustion wave circulating in there at about 5,000 hertz. So it's very impressive. And that, circulation frequency is so high when you go in and look at the exhaust flow, which is the one I couldn't get them to run all together here. Don't do that. I really wanted to show that. One more time. There you go. Now you look at the exhaust flow, and that's the only one I'll turn on here. You can see that's a Schlieren through that exit. It's pretty steady. So first time I saw that, it's like, I could actually put that in a ground-based engine, right? I don't have to worry about trying to recover an unsteady flow, because it's almost steady by the time it gets there. Question?
How big is this?
The one that you looked at
is
about yay big.
Like that's the diameter?
Yeah, that combustor. And the heat release, I'm sorry I can't remember the heat release rate, but it's very high, as you'd expect, right? I mean, there's a tremendous heat release, high-speed combustion. So these devices have a lot of potential. That's why we are starting to look at them and figure out, can you put it in ground power? Look, before you start celebrating, don't forget I haven't told you how I'm managing the inlet. Another story. Question? Yeah, the question was, are there significant mechanical stresses on the material? Yes, but nothing that's not manageable. I mean, and really a lot of the work here is not our own work, it's Air Force's work, but we've had long discussions about that, and surprisingly even some of the thermal stresses are lower than you would anticipate, because don't forget you have transient events bringing cold material past that same surface. So it's not impossible. There doesn't seem to be a big showstopper that way. There's a way at the top. Good and loud.
What do the emissions look like from these?
What are the emissions? Well, great lead-in question. That is the one area that has not been investigated, particularly this case. Why? Because it started from a propulsion application for military device. We've partnered with AFRL, and we're actually going to be looking at emissions from this device. They did a little bit on emissions, and I thought, oh, the NOx is going to be just impossible. It actually has not been that bad. I'm not sure how quantitative the numbers are. That's really not their forte. But the reasoning is time at high temperatures is relatively short. Right? So there's some opportunities there, to avoid Zeldovich NOx. So one more, yeah.
Explain again what contains this shock wave. Why it's not blowing through the top of the reactor like the combustor?
Yeah, why doesn't it go out the front end?
Yeah.
The difference in the temperature of the gas, right, it effectively creates a greater loss going back out the front end of the device. Now, there's admittedly some magic on the front end that I'm just not going to discuss today, because the injection makes all the difference in the world, and how you ignite it and get the detonation started and do what you want. Those are complex issues. But yeah, there's the first thing I thought is, how do you keep the flow from heading out the back end? Just do the impedance difference in the gas going out the tail end versus the front end, and that's it. So go ahead.
So how do you inject the fuel on the side or all axially?
It is all through the front end right now. Yeah,
Okay.
all axially. Yeah. I mean, these are, believe me, this is all new that we have not figured out how to design. Don't forget, if I got to do this land-based engine, I got to put gaseous fuel in there, premix it, get it in there without a flashback into a place I don't want, right? So we have some homework we're doing right now. One more, and then I'm going to keep going here. Go ahead.
Only the shock is just spinning continuously around the chamber itself is not moving. Just
Correct.
Okay.
Yep. That shock's going around in there. Is this still fun or what? You know, I'm excited about it. So, all right. So here's a few comments for you, just something to think about. You know, if you decide, hey, I want to go after this, I'm a graduate, I'm going to go try and get some research funding to pursue this. You know, you need to think about component comparison is very difficult in these systems that are unsteady. So I just drew a sketch there as a pressure gain combustor. You might think, well, I just need to measure P1 and P2. You know, I can figure out how much gain I've got. No, maybe not, right? You got a lot of kinetic energy in that flow that if you don't do any recovery, you just made the wrong measurement, because you're going to recover it in the engine application, right? So you have to think about, how am I going to make a performance measure that's consistent, that I can compare against all these different kinds of geometries. It's not an easy problem. And I really like this paper by Razi Nalam. You can take a look at that if you involve. Oh, here's that question somebody asked about emissions. Just not much work done there yet, but we're starting to get into that area. And then I talked about heat transfer and some mechanical issues, probably not a showstopper. To date, there's really been no head-to-head comparison, you know, of if I just had a conventional combustor, I put one of these in, how does the engine performance change? Just, it's very difficult to do a head-to-head to say, what's the performance benefit that I can get, okay? We're working on it. All right, so now we can have a little bit of a discussion, and then we're going to have a real fast final section here, but I thought this discussion to be important. So, you know, the different combustion research issues associated with the different types of pressure gain I described. Anybody just, I mean, I described deflagration. What do you got to know there? What's the key problem that I described? If you don't answer, I'll answer for you, but maybe somebody's bold enough. My opinion is getting the acoustics right. And the deflagration one, you have to have the acoustics couple with the flame to give you pressure gain, not destroy the oscillating, and still get the pressure recovery you need. It's a really tough problem because it's a system level problem. Detonation systems, if it's a detonation tube, what do you got to know there? Remember I touched on this. DDT. How to get it to detonate in a short distance, right? I don't want to burn all my fuel up in a deflagration. Really hard problem. Can't model that transition very well. How about the rotating one? Oh, I didn't want to go there. I didn't know what to do with that one, right? And then what about Razi Nalam's? I mentioned spinning around there. What does he got to do? Flame's got to shoot completely down that tube in a high G environment from rotation. So every one of these interesting combustion problems, interesting system problems. So now that we've laid that groundwork, I hope somebody answers my questions here, and then I'll tell you maybe my thought here. What do you think is the greatest challenge to development of this as a technology? Anybody? There's not a wrong answer here, right? Don't be shy. What do you think is the greatest challenge?
Modeling.
What's that?
Modeling.
Modeling. We can't model some of the processes. Otherwise, I could design the thing and go forward and start building them, right? It's a great comment. So somebody said controls. Yeah, how do you do the controls on this system? Somebody else? Materials, yeah. I mean, some of these, like, you know, the detonation tube, that one's going to get a high thermal load, and then you're going to go in with a cooling flow. There's some materials issues there, right? And you don't want, if you're going to do a flight application, you don't want really thick tubes. So good point on materials. Anything else? Greatest challenges. What's that?
Coupling to turbo machinery.
One at a time. What is it now?
System integration.
System integration is one that I'm always thinking about because I'm more of a systems guy. How do you put it in the system, not surge the compressor? Somebody had a...
Oh, I was just going to say coupling it to turbo machinery.
Is really the big one. And like I said, the DARPA program has made more progress on that than anybody. I hope all that goes out into the public because you'll be, I think, pleasantly surprised to see how much progress has been made there. But it's a big, big deal. Up in the corner. What's that? Oh, yeah. Lifetime of the system because you have these oscillations which might lead to high cycle fatigue. All right? You know, people are thinking about that. It may not be any worse than a piston engine, right? But you got to think about it in the context of a turbo machinery. You want to hear my answer? What I think it is? Because I think about this stuff a lot. Because I bet you I knew none of you would say it. All right? You thought I was putting a diamond in there just to be funny, right? No, there was a reason why I did that, all right? I didn't have a chance to look these numbers up. All right, I wish I did. I got to get this chart. I've seen it somewhere. I couldn't remember where I saw it with real numbers, but I'll get it eventually. So I didn't include it in your notes, but it's a real situation. I drew it up myself, so I made it big. So I don't want you taking into numbers like those are the real numbers, but they're close. All right, and so what I'm plotting here is engine efficiency versus the size in megawatts of a particular power plant. Then I show, you know, here's kind of where small turbines sit, so-called microturbines. You know, they struggle to get above 25% efficiency. There's a lot of losses connected with them. That's why where people use microturbines, they typically use them in heat and power, right? They use the exhaust heat to do something else like heat water, that type of thing. That's where you want to use a small turbine. If you need small power, I wouldn't buy a turbine. I'd go buy a recip engine, right? Less than a megawatt. They're just way more efficient, right? So they're sitting up in here. Some of these things are approaching 50% efficiency. And then you start to get to simple cycle turbines like aeroderivatives, things that were derived from aircraft engines. And some of these are pretty remarkable, LMS 100 and so on. I mean, they're getting up to 50% efficiency in a simple cycle design. And they're up in the tens of megawatt range size, right? Pretty big machines. And if you want to do base load electric power, combined cycle turbines, those things are now up above 60% efficiency, all right? So that's kind of, you know, if I was going to go buy a piece of equipment to make power, I got to know, well, what sizes make sense? What efficiencies are the ones that I'm interested in? And so, you know, I asked the question, what's the greatest challenge to developing pressure gain combustion? You know what it is to me? Where's it going to fit on that map? Because if I was going to develop this, I probably wouldn't sign up to build one at 200 megawatts my first try, right? I would try to build the smallest one I could down here, right? And if I got 5% gain in efficiency, you know what? It wouldn't be any better than a reciprocating engine. And people would sigh a collective yawn and say, what were you thinking? Why did we give you that several millions of dollars to do that? It makes no sense to us. They would be right. Huge challenge. I don't know how to build the first one and get somebody interested because of the competition. And really the message I'm trying to leave with y'all as researchers thinking about technology development, know the competition. You can spend 5 years of your life developing the greatest technology. Maybe some of you are going to be an entrepreneur and you weren't reading the paper and following literature and somebody came along with a competing technology that just ups the ante and your idea is not that good anymore. It's really disappointing. It's happened to me. Probably happened to some of you, but I try not to let it happen. So believe me, in pressure gain, we are busy thinking about this chart. I can't figure out how to get around it because I know the biggest impact is going to be out in here. Remember that comment from Mike Idlechick, VP at GE? Said, yeah, 5–10% gain, first application, land-based power. You know what he was thinking about is here. But he's having trouble getting the $200 million he's going to need to build a full-scale version of this too. So this is a challenge for us as a combustion community, is to articulate this idea and push it forward to development and get it to the scale that makes sense. But somehow we got to do that, realizing the first few are not going to be the big performance gains because they'll be competing against recip engines. Question right there.
But couldn't the small scale engines, just like all of our experiments we do on small scale, give you a lot of insight into the performance benefits of big ones?
Oh, absolutely. And that's the argument I'm sure we're going to make. I'm just pointing out to do those small scale tests even, you've got to get enough funding to move it along, and then the next person's going to say, oh yeah, but that was in a small engine. That'll never work in my 100 megawatt engine. I'm just giving you a hard dose of reality. And I think what will happen is what you just described. We'll see these tried at a small scale, but I don't see a big market for them. And so I'm just giving you all an insight into how technology development is really going to occur in some of these energy systems. Any other quick questions here? If not, okay, stand up. Take a, 3-minute break? You do that for 3 minutes, and we'll do one more fun topic really fast and get out of here. I can't do it. Tried hard when I put the notes together. If you're really interested, you can find the citations, and you can even follow the derivations. I mean, I've derived them all myself, and as best I could, I made sure there weren't any mistakes. You should be able to follow through the derivations. I still do make mistakes. If you find one in there, call me out because I want to know and correct it because I'll be using these slides for other things. But I'm pretty sure all the equations are correct in there as I rederive it myself. So we're going to talk about, I use the word a frontier approach. We covered the issue of oxy-fuel combustion. It's a disadvantage because you have to make oxygen. So I'll try chemical looping. But I kept thinking and thinking and thinking about that, and I said, I'm going through this process of making oxygen, and it's kind of interesting if you're like a chemical engineer or something, because pointer here. In conventional oxy-fuel combustion, you take that stream that you spent so much time and effort to make pure oxygen, and then you go dilute it down again. And that's just not right. You did all this work to make pure oxygen, and then you dilute it. So this last couple of years, I'm thinking, there's got to be a way I can take advantage of the fact that I put all that energy into making pure oxygen. How do I do that? It's not a completely foreign thought, right? There are technologies that rely on having pure oxygen, right? For example, if you want to do process industries like make steel or glass, they do oxygen combustion to get the very high temperatures to drive that process. It's a big advantage. If you want to make rocket engines, you have oxygen supplied to those engines for reasons of how it affects propulsion and the mission you're involved in. People do that, all right? And so the question, we've been asking is, well, isn't there some way I can make it an advantage to do oxy-fuel? I'm not just worried about catching carbon dioxide, but I want to have an advantage by going to pure oxygen combustion. And then if I want to catch carbon dioxide, it's easy to do. So how would you do that? Well, that's an interesting thought. And if you take a look at a plot of efficiency on one axis versus different temperatures for different kinds of combustion, gas turbine combustion actually has fairly low temperature combustion, even compared to pulverized coal. But this is the temperature also of the working fluid. And so you get high efficiencies in, for example, a combined cycle, point D up there. If I did pure oxygen combustion, oh my goodness, the temperatures, they're up actually a little bit higher than that, right? So I have the potential for very high efficiency, but I don't know how I'm going to get that potential converted to work, right? The turbo machinery, I'm limited there. How in the world am I going to take advantage of that and generate power? Well, it turns out there is a way to do that. It's called magnetohydrodynamic power generation, and I'm going to be a little bit picky and swear you all to agree with me. You won't use the word magnetohydrodynamics in the wrong way, which it's been for 30 or 40 years, to describe power generation, because magnetohydrodynamics is a scientific discipline. Power generation is something else. This is one way to do it. You'll understand why I'm being picky about that in a minute. But let's talk about MHD topping cycles. First of all, a little review here of how you make electricity with a conventional generator. You have a magnet, and then you have a wire that goes through that. And as you push that wire through a magnetic field, it forces the electrons along that wire, and that's how you make electricity. All generators work that way. Well, you could do the same thing if you had a hot conducting gas and you pushed it through a magnetic field just like a wire if that gas was conductive, and as long as the ends of that gas were touching two electrodes, you get power out. It's no different, right? The only thing that's changed is instead of spinning a copper wire, I'm pushing a conductive high-temperature gas through that environment, and I'm extracting electric power. Now, on the surface, it sounds kind of appealing for high-temperature environments because I don't need any turbo machinery. The work just comes out directly from the fluid. The turbine is the electrodynamic interaction of the flow with the work that you get out of the fluid moving through that environment. So that's how this process works. And if you think about how you would actually do this in a real application, the idea is you have this topping cycle here, which is the MHD power unit. Again, you need oxygen, so you put the air separation in there. You take part of the power out of that MHD unit, drive the air separation unit. Some work then you want left over to produce energy that you're interested in. And for reasons that I'm going to explain later, you have to stop extracting power out of an MHD unit when you drop down to about 2600 Kelvin. And at that point, you can dump into basically a conventional boiler and have a bottoming cycle. So what's the combined efficiency? What's the possibility that I could achieve efficient power generation from this combined system? Well, you can just work through the algebra here if you've never done this. The combined cycle efficiency for a topping unit and a bottoming unit is the sum of their individual efficiencies minus their product. Okay, so just add up what's the efficiency of this unit to the efficiency of this unit minus their product. So for example, this bottoming steam boiler could get up to 45% efficiency with modern technology. So what can I get out of this? Now don't forget, I got to supply some work over here. Optimistically, you might extract about 10% of the enthalpy as work. That's still pretty good though, right? Because if I have a topping system with about 10% enthalpy extraction, bottoming cycle with 45%, the combined cycle efficiency is 50%. So suddenly I've got a product stream here, which is CO2 and water, easy to get the CO2, yet the efficiency of the power plant went up. That's what I wanted to do, right? And the better I can do at this topping efficiency, the better it gets. Well, how good could it be is an important question. Let's take a look. This is not a new idea. There was a very active program on magnetohydrodynamic power generation back through the 70s and then on into the 80s. When I read of those historical documents, frankly, I think the work in Russia was a little bit further ahead because they started with the intent of doing natural gas. It's easier to do with natural gas. And you can see their particular MHD tube right here. And this thing actually ran and produced some power. It was located outside of Moscow and was online for actually some time. I don't remember the exact numbers. And then the Department of Energy, we sponsored a program which ended in '93. Huge program over that period of time. Not quite $1 billion, but getting close to it. And that's in those years' dollars, not today's. So big program to develop it. And we succeeded too in putting power onto the grid. But it didn't work out well. There was an economic downfall. The electrodes were damaged. Seed materials got to be a problem. I'll explain what that is in just a minute. And so the program ended in about '93. And frankly, it was pretty much forgotten about. And then we started thinking about, me and my colleagues at our lab, and started reading that earlier literature. We said, wait a minute. We know we did this, and there were some problems, both in the US and then in the Soviet program through the 70s and 80s. The thing worked technically, but the electrodes just didn't last long enough. You have to go and keep replacing electrodes. So I said, well, there's other technologies. At that time, IGCC, natural gas combined cycle, were just starting to emerge. So the competing technologies ended up taking the day. And this program was stopped. Again, what I said before, be careful you understand what the competing technology is, because this lost, those won. But what's happening now, we'd like to have CO2 capture. There's been a significant development in the air separation units that make that oxygen, the energy needed to make that oxygen. has dropped down substantially since this program because we've been interested in oxy-fuel combustion. Magnet technologies advanced fairly substantially, largely due to there's some big atomic collider in Europe, CERN. They built some really big magnets there, high-power magnets. So we think because of those increases in magnet, we can increase the power density in those tubes substantially. The thing that I think has changed more than anything since that time, prediction capability. That was the one thing we realized is way different today than it was at the time this was attempted. If you go back and read that literature, almost all the development was experimental with some modest attempts at modeling and reduced order modeling to understand the physics of what was going on in those MHD tubes. And when you see what processes that are involved here, you'd think these guys must have been geniuses because it's really complicated and they got it to work. A lot of cutting and trying though, right? So we think there's a reason to go look at this again. And beyond just what's happening then and now, we think there's some next generation ideas that really merit taking a look. Go ahead.
You assume that there's a high degree of ionization.
Yes.
So do you have a feeling of charge density?
We're going to cover it right at the end here because you're actually going to have to see the flows unless there's something new going on. I'll talk about that in just a few minutes. So thank you. Great question. Let's take a look then. Oh boy. Now, like I said, we're not going to have time in a half an hour to cover all these details. So I'm going to do is just cover the first half and explain the physics because that's all you'll be able to get. But I think the physics are actually pretty easy. So don't worry too much if we don't cover all the math details. You get the physics about what's going on here. You know from is this volume okay up there? Yeah? All right. You know from some of your introductory physics class, electric field, you put a charge in it, creates a force on that charge. I show that down here. Electric field times that charge gives you the force that's trying to drive that charge in one direction. Less well understood or appreciated, if you have a magnetic field, a vector going in this direction, and you pull a charge in the direction of that arrow, that magnetic field will try and force that charge down, right? That's how you generate electric power in a copper wire, right? You push that wire through a magnetic field, electrons get pushed. It creates a voltage potential. So there's the force on that thing, and lo and behold, if I take that magnetic force and divide it by the charge, U cross B is equal force divided by charge, it has the same form as an electric field that we're familiar with, so it's an induced field. All right? And I actually have a physics degree too, so this was really familiar to me. It may not be familiar to all of you, but I still struggle with the idea that there's an induced field. Notice there's no property value in there, U by B. But that's it. You can go in and read the physics books why that's the case. All right? So there's an induced field by motion in a magnetic field. That's the key point you got to remember. All right? So let's see what happens here. Could you turn that notion into an electric generator? So I'm showing here a duct, all right, with some gases that are flowing in, conductive hot gases. They flow through this duct. This top surface here is an electrode. It's connected by a wire to this external surface. There's a bottom, electrode over here. So the velocity comes roaring through in that direction. The electric field, the magnetic field B is along this axis. Remember what I said? There's an induced field from the combination of the velocity and the magnetic field, their vector product, and that with the axis coordinate system I've set up here is U by B, negative in the K direction. Right? So down in that direction. J, I've already found a mistake there. J, that's how they're pointing down in that direction. Correct your note there. I'm sorry I missed that. That's a J right there. All right. So what that does is it creates an electric field pushing the electrons down, and it can drive electrons through that field. All right? Does that make sense? I apologize I put K instead of J. Pay attention. So it's going down in that direction. So that's how this process works. Makes an electric generator. Yeah?
Where are the magnets in this?
Running in this direction. You have the north pole here, south pole here, running across that way. Okay? Big, gigantic magnet. How's that similar to a conventional generator? With a wire? The wire takes the place. You can imagine standing a wire up in here, right? Going between here. Pushing it down that tube. That's how it would work. Does it make sense how that works? The same thing as just having a wire flying down that tube. touching both sides, and that's how you generate electric power. All right. Well, how much current flows? Oh, we're not going to have time to take you through the algebra, but you can follow it through here. The current that's going to flow, that's current density, in other words, the current divided by the area, is equal to the conductivity of the gas times the net field, the net electric field, which includes both the field that's applied from an outside source as well as that induced field U cross B. If you work those vectors out, again, there's a J over there, not a K. This time I got it right. Put those numbers in there in this one-dimensional problem. It's that electric field from the outside minus the product of U and B. And I show those vectors schematically here. Here's the electric field from this external circuit, right? High voltage in the bottom, low here. The vector is pointing in that direction. Here's the UB product pointing this way, and the current is flowing in that direction because this vector is bigger than that one. All right? Now, if you want, you go home tonight, you can actually plug these numbers in. I did it. You know, it all works out. You find out that the current that flows is equal to something, the open circuit voltage, but if I took that off, divided by the internal resistance and the resistance of the load. The internal resistance we'll get to in a minute. That's the resistance of electrons flowing through that plasma. All right? It's just like a battery, right? If a battery, you're running a battery, you can put an external load out in here. You also have internal resistance. As soon as you start pulling current out of it, there's resistance to that flow that exists inside the battery. And so that's what's accounted for here. It's not very complicated, really. All right? You have the driving force comes from the magnetic field, and then you have the current on the outside, which establishes that electric field. And so I just put some limiting cases here. Just these all make good sense, I think, if you just have even first class in electrical engineering. Open circuit, the electric field is balanced by the induced field from the magnetic. That one points that way, that's going there. There's no current flowing because I have open circuit, and the open circuit voltage is given as I have there. As you start to add resistance, you start pulling current through the system. This field starts dropping as you start to bring the potential closer. You're driving more current through. And finally, if you just short circuit it, there's no voltage difference between those two. If you connect them, there's no electric field from the external environment. It's all the current is driven by that magnetic force pushing the current around that loop. And so there are the limiting cases. It's a very simple generator. It seems complicated, but not really too hard. We're not going to have time to go through all the different cases here today, so I'm just going to look at the clock and click through a couple things that are important and get right to this point here. I just showed you that you can generate current or current density in that y direction as a difference of that applied field and the induced field. Now, we won't have time this afternoon to go through the unpleasant reality that the current doesn't just flow straight up and down as I described it. It's a gas full of conductive material with electrodes on the outside, and the electricity is free to go where it wants to based on the field it experiences. And this part, it gets complicated, all right, by something called the Hall effect. So again, what I'm showing you here is this velocity of this gas. This isn't connected to anything yet. It drives this induced field, which sets up, in contrast, it sets up a voltage potential between those two plates. And then as soon as I start getting current flowing from that environment, the electrons, they go against the direction of current flow, they start flying up to complete the circuit. So now I have electrons moving in a magnetic field. So now I got another direction of motion I got to worry about. The electrons are going up. The velocity of the gas is going this way, but that electron current going up interacts with the magnetic field, and it experiences the force going which way? Backward. So you drive, by the fact you're trying to get a current to flow upward, you end up driving current in the other direction. It actually goes back that way, the electron current. Electron current and current have two different signs, you see. You're going to get confused a little on that. The electron's actually going to go back in that situation. Turns out that is a huge detriment to the performance of the whole generator. Why? Because you're just driving current back through the gas, which has resistance, putting it back into the electrode at the top and it just goes around again, you don't get much power out. It's a disaster for the system. You need to do something about it, right? So let's just skip ahead a couple here. This actually takes you through the details of why that's a problem. What do I do to get rid of that current that's trying to sneak back upstream in the generator? Well, there's a real easy solution. Just break up the load, right? So I'm showing here this tube is going along in this direction. The flow is going here. These are the black, squares show where I'm trying to collect current. And I just collect my external load up to each one of these. And you can't get current going in this direction. It has nowhere to go. You can get a big voltage potential, but you can't get current flowing because it's not got anywhere to go. Right? So there's a big voltage gradient. But it's a great idea. And in fact, if you go through the notes, you can completely eliminate the loss that I described from that current flowing back from the Hall effect. Great idea. One big disadvantage. Take a guess. What is it? If I break all that out and put all the electrodes in there? What's that? Cost is going to be the big one because there could be hundreds of electrodes involved on a typical tube. These tubes are, tens of meters long, and so you got these hundreds of electrodes. Each one of them has its own individual load at a different voltage. Probably not what you're going to do in practice. You have to have control on every one of those guys. So this isn't probably the way it would be built, but it's interesting to understand. You can get around the problems of the Hall current, and there are different concepts to avoid that loss from this Hall current. And we're just not going to have time today to describe what some of these are, but the key point here is you can configure the electrode geometry to actually take advantage of the Hall current. And this one is called a disk generator. Very interesting concept. I'm going to describe it. You might not catch it, but you'll get the physics of what I'm saying, and you can go back in later and maybe look at how does the vector mechanics work. It's actually very straightforward. But the idea here is the velocity comes in and goes out radially, right? So you put the magnetic field in this way. U cross B then drives a short circuit through the gas running in this direction. So I have current flowing around that annulus. That current is interacting with the magnetic field as well, and it actually drives the voltage between these two electrodes. So it's an interesting idea, right? So I'm using the short circuit going around this way to interact with that electric field and then drive the potential that I'm collecting across how many? 2 electrodes. I love that, right? Because it just cuts down the number of electrodes. Very interesting idea. Practical design will be more than 2. They'll probably pick up a couple so don't get too high of a voltage potential. But again, the point is you can get rid of some of the influences of this Hall current, and you can still recover the electricity, small number of electrodes. So great advantage here. And you'll see at the end there, ask the question, if you're really clever, what happens if you add swirl to that flow? Actually, if you read these notes, you'll be able to figure it out. 1 minute, draw a picture, you'll see what happens if that flow is swirling. Can completely counteract the Hall current with a swirling flow. So you can draw a picture just with a couple vectors and you'll be able to show that. It's a very interesting idea. There's other approaches, slanting the current pickups, slanting the field along there. Again, we won't have time, but this was actually the one that was probably most likely to go commercial back in the earlier programs. You can see the electrodes slanted in that duct as you're going down. What it does is it puts an axial electric potential into the flow that keeps the Hall current in check. And so this was an idea that was really pursued pretty aggressively. These are just interconnected within device, but you only have a couple of loads, so it gets around this problem of having a lot of different loads to control. So these things were built and tested in that earlier program. Time-wise here, I got 3 minutes. Oh boy. Not going to do this in 3 minutes, guarantee it. But you can take a look at, you can just, I put some citations, you can derive the fluid mechanic balances that you need to and convince yourself they all make sense. And by the way, if you go through and do that, I did notice the crossbar on volume dropped out in the final print here. You can cross that if you're interested, so it's distinct from voltage. So just put a cross through there because I just happened to use V for both of them, and then I saw it, the cross dropped out one. One question, yeah?
In this configuration, are you not diluting the oxygen at all?
I'm sorry.
Are you not diluting the oxygen?
Are you not using the oxygen?
So you have the oxygen, but you're not going to dilute the CO2?
Correct. You
Aren't you
want
gonna have an
full high temperature oxy combustion.
At that-
3200 centigrade. Unbelievable.
You
Like a
have-
rocket engine.
Do you have a particulate emission problem with that temperature in the diffusion plane?
Good question. You have a particulate emission. Right now, these would need to be seeded flows, and it's explained in here. Because we're going to sequester all the product stream, you're going to cool it down. I'm not worried about I'm not even worried about any other emissions at that point because I'm capturing all the exhaust stream. And that's what's fundamentally different today about potentially using this technology than when they did it in the late 80s and late 80s. Because there they were planning to send whatever the flue gas was up the stack. A lot of money spent trying to make sure we didn't have any of the seed material going outside the system. Well, you're not going to have that if you're going to do CO2 capture. You're going to condense that whole stream. I guarantee you would probably do it with a wet condenser. It'll all wash out. And so, again, because the drivers are different, we're looking at this thinking, maybe this makes some sense to look at again. But it's not without its own set of problems. I'm going to skip over the details. By the way, in terms of modeling, all right, so here again, we're not going to have time to cover the different equations, but these are the electrodes. They're segmented here, picking up current from the flow, all right? And there is a strong force in the momentum equation, that JB term right there, that is holding the flow back like a turbine blade is trying to hold flow back. All right? Now the interesting thing is, it's absent where there's no current flowing. I mean, you think about that fluid mechanically, wherever you don't have current, if for some reason that fails, the fluid can jet through that region because it's not facing that body force. It's an interesting problem fluid mechanically, and frankly, our CFD people are going back and looking at the assumptions and how you describe the boundary layer, the wall conditions, all those things, because I just don't think we really know how to treat a problem correctly where we have this body force, which is depending on the current flow right in that vicinity. So it's a really interesting computational problem, and we're going to be doing a lot computationally before we ever do anything experimentally. So let's go on here. Here's just wrap it up here. The reason this idea can work compared to other generators, the conductivity of the gases are very low. Even if you put a seed I'll describe in the next slide here, the conductivity of these MHD flows is 10 Siemens is like reciprocal ohms, 10 Siemens, whereas a copper wire is orders of magnitude greater. How in the world can that work? Well, I'll tell you how it can work. If I do it in this system, the MHD system, the velocity is about an order of magnitude higher, right? Kind of a supersonic flow. The volume that you're conducting through is about an order of magnitude bigger, right? Because you're conducting through that whole volume, right? So you put those two together and you're already up a couple orders of magnitude. So it can actually work. It can be practical, but you have to have this kind of conductivity. So is that realistic? Well, turns out, and here's how you get to that number of 10 Siemens. I won't take you through it. This is a conductivity of gases versus temperature, where I've put in, and I think this was a potassium seed. If it was not seeded with potassium, you wouldn't even have conductivity showing on this particular chart. So you got to have high conductivity flow. This is enough to make it practical because of these big volumes and high velocities. So it's likely you're going to seed the flow, what I'm telling you. You've got to recover that seed. Again, with carbon capture, the question that came up earlier, it seems likely you can do that. So seeding is one of the big problems in the earlier program in terms of cost. Again, because of what we're doing today to capture things, probably not an issue. The electrode pickup, that was an issue. You can see here's an electrode from some of those earlier tests. They ended up burning it off. It's probably less of an issue if you start with natural gas. This was with coal. Coal has other issues. We don't have much time to talk about it again today. We're almost done. That's what it would look like in a power plant. Let me just take you one more thought. Today, one of the main things different, look at the size of the inverter building. But don't forget this makes DC power. You know that there's a real interest in high voltage DC power now in the U.S.? A lot of people would like to see the grid move to DC power. Sorry? Yeah, I mean, there's an interesting point that this makes DC power. You might avoid the inverter. So a lot of reasons to look at it. So here's a few comments here. You can go through and the key thing is how much can we actually get out of this. There's a great review article. And one of the things we're looking at is, can I do an unsteady version of this? Something completely different, and that's why we're trying to coin the phrase direct power extraction. Nobody's been able to tell me how much conductivity I could force behind a detonation wave. Nobody's told me. I've asked a bunch of people. I got a bunch of extras. I wish somebody would tell me. We've actually been measuring it through the Air Force, but I'm wondering if I can jump it up in some way we haven't thought of yet. I'm off thinking crazy things that we can do it. But one of the things we are trying to do is just get a valid simulation of what's been done in this area, because there's very little there. It just wasn't available when we did this program. So we're actually off trying to do that right now. And I just have to tell you this funny story, and then we'll close. So we said, boy, if we're going to get into this area, we really would like to simulate it first before we invest a big chunk of change and research. And how are we going to simulate it? And the next question is, where am I getting data to make sure that even one simulation I do is correct? I mentioned that earlier, program at DOE ended in '93. And so we said, well, if I could just get the data from that program, which was run by our lab, okay, that'd be great. So we started to go look for it. We couldn't find it. And my best guy, Roger Woodside, he went all over the lab. He was looking around for it and records retention, and it just seemed like we couldn't find this repository of information that we knew existed somewhere in the lab. And sure enough, he found it behind some storage containers in the place it should have been, but it was just somebody moved from container. He found the thing, and he pulled the first label off, and it was slated for destruction 30 days later. Talk about good timing, all right? We would have lost, because I mean, it's very old. We only keep things for so long. So in just a few days, we have an undergraduate student who will be opening the remaining 8 boxes. I've been through the first 10, all right? I'm done. All right, so he's going to go through 80 boxes. So when you think of this area, just remember there's this one young man who is today, all this is, he's going through it, he's going to help us figure out which of these are valuable, which data can we use, and we'll be making some of this available, probably digitizing a lot of it. So if you decide, you are interested in this, please give me a call. It's an area which I'm just telling you up front. We're going out on a limb here. We may get told, you guys, gone way too far. But what better place to talk about it than here? New frontiers, right? Energy. So anyway, I'm done. I've talked too long, but I'm happy to stay and talk to you all. But I'm just going to wrap it up, and y'all can go to dinner. So thank you. It's been a great, great hour.